Alright everybody, welcome back to my YouTube channel. So in this video we are going to learn about polynomial regression. So at very first we are going to learn some theory about polynomial regression, and then we are going to actual implementation of polynomial regression. So let's get in. So polynomial regression. So basic idea about polynomial regression is that when we have data or some kind of information which is like roughly like straight line. Here it is in A and B, the data is in roughly straight line, but where okay, when we have roughly straight line, then we can apply linear regression on it. But what if we have the data is like some curve format or like parabola type or like hyperbola type, having or so many data taking curves, etc. So for that reason we couldn't apply linear regression very well, because applying linear regression there might causes problem like overfitting and or underfitting. So for that reason we are going to implant polynomial regression. So take with an example. Suppose we have study hours as 0 hour to 8 hour and marks as 30 marks, 45 to like 83 mark. As we all know that guys, at some point marks are going to be saturated, because it is not like that when we study too much then we got so many marks, but at one point like 93, 94, 96 marks are going to be saturated there. So the whole arrangement or visualization of that data might look like this, like curve like this. So applying linear regression on it, it is not the suitable approach. So we are going to apply polynomial regression. So at very first, so let's clear about polynomial regression. So polynomial regression means regression in which we are considering degrees or points to break the curve into several points. Suppose here I have break it into 1, this is 1, this is 2, and this is 3. So this is how we are going to cut the graph between 3 points, like first point, second point, and third point. Then these three segments are straight line, behaves like straight line. This is a brief idea about polynomial regression. And then we have, so this is y is equal to ax plus b. This is the formula of linear regression. Let me check the video is on. Yeah, yes it is. So y is equal to ax plus b is the linear regressions formula, but when it comes to polynomial regression we have y is equal to ax plus, this is for degree 2. This is actually linear regression having degree 1. So why when we go to degree 2 means polynomial regression, we got to add an term like x square. So b is input and x is here weight, here is weight, x weight, x square is weight, x cube is weight. Weight means the slope of that line which we have broken into segments or implanted the points on it. So and this is for degree 3. Observe it in this expression, as the degree increases the weights order or weights power is increasing along with it. So this is what the formula of polynomial regression looks like, and this is what it is for degree n. Shh. Keep quiet. अरे शांत बसा ना. Just leave it as it is. So now we have another example called age, which is x is equal to age is 20, 30, and age is square and age is cube. So this is not an example actually. So okay, right here. So with degree 1, y is equal to mx plus c, which is linear, and when we got y is equal to mx plus b x square plus c, which is parabola, means for degree 2 it might be or it must be parabola. Then as we increasing decreasing degree, then we have for degree 3 the curve might have two bends actually. For degree 5 it is very flexible. Okay, we are pausing. I have paused because of the background noise, just ignore it. So for degree 5 it is becoming very flexible. then let's what imagine about degree 2. It might be very flexible or extremely wiggy, like spring. It is like boom boom spring. So at another slide we have, okay, for degree 1 it is straight line, degree 2 it might have two bends, for degree 3 it might be like hyperbola, etc. Degree 10 it might be wiggly or extremely sloppy. So this is all about so okay, what we have written here, in one in degree 10 it might be look okay. So I will tell it to you at further. So advantages of it are, can model non-linear relationship. Okay, means non-linear relationship are getting to be curves or the bends, etc. Accurate than straight line. Okay, it is accurate than straight line in some cases. Easy to implant in scikit-learn, and disadvantages are okay. So these are disadvantages, which is extremely sensitive to outliers. Okay, it is extremely sensitive to outliers because when an outlier got, then the curve might be stretching out there for to obtain or include that point, so that it is extremely sensitive to outlier. High degree can overfit. Okay, I have discussed it. Choosing right degree is important. Okay, then at last we have where we should use it in population growth, temperature prediction, or like exponential things which we are going to implant. And the last one is the basic implantation. Okay, so this is all about the first one, textual approach, or the theory about that polynomial regression. Now let's get into actual example. So for that reason I have one CSV here, right here in machine learning's directory, polynomial regression and the polynomial data. Let's copy it as a path, and I have started Jupyter notebook here. Yeah, I have. So let's get into it. Stop in machine learning, polynomial regression, that right here. Just remember that I have done previously. Okay, it is so data. Okay, let's start from here. First, importing pandas, taking a look at data. Okay, so this is what we have for data, which is x. Let's take it as x, suppose b, it is feature and y is target. So we have x and we have y, which is of 180 rows and two features or two columns. Okay, let's first visualize it with matplotlib that I have told you or taught you previously on my YouTube channel. If you are interested, you can take a look on that. Plot. Okay, so this is what we have data. So in this data it is looking like curvy, but we have to just break out here and then here and then here. So first 1, 2, 3 and then 4. So we are going to take degree 4. Let's get into it. So let's split the data into x. X is equals to data frame of at x, and y is equals to data frame of y. Okay, now we are turning and testing, splitting the data with 0.2's ratio. So scalar dot model selection, import train and test split. Okay, X train, X test, Y train, Y test is equal to train test splits of X and Y with test size of 0.2. Okay, now the CSV is of totally 180 rows, but we are splitting it into training and testing section with ratio of 0.2. Let's check the length of Y. Okay, for training it is 144 rows and remaining rows are for testing. Okay, let's scale the features now. Scalar dot import from a scalar dot pre-processing, import standard scalar, and then we have x train scale is equal to scalar. Okay, sorry, my bad here. When we import scalar, we have to make an instance of it, because in some cases we are going to save the scalar with job lib, because we are using it in app development. So making an instance of scalar, which is scalar is equal to standard scalar. Okay, I missed the parenthesis here. Okay, scalar dot fit transform X train. Okay, so expected two-dimensional, blah blah blah. I got you. So we just have to make it two-dimensional so that it can be scaled easily or debugged easily. Not right here. Yeah, right here. Note that, guys, we have to make it two-dimensional in most cases, but not all the cases. But it is good practice that you are making it everywhere. Is this extreme scale? Okay, let's debug it. Extreme scale is equal to scalar dot fit transform X train. Yeah, I got to be used here also. Yeah, now we are good to go. Now we have X test scale is equal to scalar dot transform X test. Let's print X test. I spelled right. It is not X test scale, it is like, yeah. So now we have scaled the values, and then we are going to implement the polynomial regression. For that reason, we are required of three libraries from a scalar, which is pipeline, make pipeline from pipelines module, and then second one is linear models, polynomial regression, and third one is from pre-processing, importing polynomial features. So let's moving on from distractions. Okay, now we are going to implement the polynomial regression. For that reason, I am here including from scalar pre-processing, import that polynomial features. Now we are importing from scalar dot pipeline, import make pipeline. Now we are importing from scalar dot linear model, import actually there is not polynomial regression, it is linear regression. Yeah, so we are actually using linear regression, but from pre-processing we have polynomial features class in which we are using the breaking points or degrees, so that lines are bending or breaking at that points and making straight lines to cover that graph. So we have imported that required libraries. Then we are making a model which is we are making pipeline of that polynomial, in which we are using polynomial features with degree. I think we just require degree of 1, 2, 3 and 4. Yeah, so we have required degree of 4, and then we required, we're good to go like giving linear. What happens to my debugger? Okay, is one I have to just give this comma. Yeah, okay, linear regression. So take a look here, right here. I have make an model with make pipeline in which I have passed the polynomial features. Degree is 4, and the model is working with linear regressions. Okay, it is totally polynomial regression, but we gonna require linear regression class. So for that reason we have made a model. So let's fit that model. So like model dot train. Sorry. Fit. We are going to explain scaled and y train. Okay, now we have train and model on that data. Okay, with features. Okay, we have thrown actually very far. With features, this and this parameters contributes for linear regression with learning rate of 0.6 times 0. Then one job not required here actually. So let's check the accuracy of that model. Model dot score. Now we just passing more x. Now we are passing model x test. X text. Sorry guys. Sorry for that background noise. Actually, what? Let's make first y print. Y print is equals to model dot predict x test. I got typo here actually. While x test L. Okay, no worries at all. Now we have y print. Y print. So let's import matrices model. Matrices. Import R2 score maybe. Yeah, it is. Score. Now printing that model. Score y test comma y print. Okay, here it is. And now we got R2 score of 0.95, 62, 61, which is quite great. Even the R2 score many more like 99, 98 is lead to be overfitting, but 95 is actually great. Means out of 1000 inputs, we are going to predict 956 outputs very correctly, and the model is simply not going to overfit it, because we have done it very well. So this is all about today's video. We have we have covered polynomial regressions theory and polynomial regressions implantation in today's video. Kindly very sorry for that background noise. Thank you.